Okay, so good morning to everybody. It's a pleasure to see you all again. Today we are meeting to listen to Gladston Duarte. He is from the AGH University of Science and Technology in Poland, and he's going to talk about invariant manifolds near L1 and L2 in the planar elliptic restricted three-body problem. So we are all ears for you.
Okay, thank you very much, Professor Felipe. So good morning, good evening, good afternoon. I don't know where everyone
Please turn off your cameras, sorry.
Yes. Good morning, everyone. Good afternoon, good evening. I will talk about work I developed in Barcelona during my PhD. In fact, it's part of it. We did some computations more. I will refer to them. In case anyone is interested, you can have a look on the preprint that got accepted last month. And also my thesis is available online in case anyone wants to give a look at it. And yeah, that's it. That's the summary of my presentation. I will start by motivating why did we study all these things, and then two models in celestial mechanics: the planar circular restricted three-body problem and the elliptic that we used to model this problem. I'll state, and then we'll see how these tools and the computations we did can be applied to understand the dynamics of a comet called Oterma and the dynamical objects in the elliptic RTBP, which is the novelty of these research. So I'll just start by stating the problem. There's a comet called 39P Oterma that has an interesting dynamics because of gravitational interactions with Jupiter. It jumped between regions in the solar system. That's it. Its orbit. It's better seen when it's projected to the XY plane. So let us see it here. Oterma's orbit is in red and Jupiter's in green. And Oterma is in some moment of its trajectory. It's a comet that orbits the sun. So in the moment of its trajectory, it's in the region between Jupiter and Saturn. But because of gravitational interactions with Jupiter, it jumps to the region between Jupiter and Mars. Stay there for a couple of decades, and then because of gravitational interactions with Jupiter again, it gets back again to the region between Jupiter and Saturn. Can you see my mouse if I point here, or can't?
Yes.
Okay, so here, Oterma is here, interacts with Jupiter, stays here. Mars orbits should be around here, and Saturn should be around here. So Oterma stays here for a couple of decades and then gets to the regional region again. This problem, this orbit, was studied using the planar circular restricted three-body problem, which is assumes that you have two massive bodies, in this case Jupiter and Sun, and a third massless, we consider massless, and then the problem is this massless body is its orbit, it's in the same plane as these massive bodies, and the massive bodies describe a circular orbit. And the problem is to compute the orbit, the dynamics of this third body. Sorry. It's a Hamiltonian problem, and it's Hamiltonian. It's written in this way. We are using x and y as coordinates, px and py as momenta, and mu is mass ratio between Jupiter and Sun. In 2001, this group of people, they described what is who are the responsible for this transition behavior. We set ourselves in a system of coordinates, which is called synodical, that rotates with the same angular velocity as Jupiter and Sun, so that they are still in the same, they are in the same points, they do not move. And there are some results about this system of coordinates. Some of them is that you have 5 equilibrium points, 3 aligned with Jupiter and Sun is here, Jupiter is here, and 2 equilateral. And around, for some energy values of this system, around these equilibrium points, there are some periodic orbits. And these periodic orbits have stable and unstable manifolds. And these manifolds are precisely the guidance to this transition behavior. What happens is that these are tube manifolds. So imagine you have a periodic orbit and this has a stable and an unstable manifold. So these are tubes. Imagine that if Oterma, say for instance, is inside this tube, it will follow this tube and will enter this region here. And if at the same time it is inside this pink tube and this red tube, it will experience a transition for this region here. It can be better seen when we compute Poincare section here. Recall that this is a projection in the configuration space, so we have more dimensions here. So we have the opportunity to describe, to compute the Poincare section here. And there are some energy levels where you do have some intersection. Let me give you a zoom just to see it clearly. And there are some energy levels where you don't have it. So depending on the energy of this particle, we can experience a direct transition, because of course it can have some revolutions about Jupiter and after it enters, but Oterma do not. Oterma goes around rapidly. It do not revolve around Jupiter. And it's because this intersection, Oterma is inside here or here. Okay, so one might think, great, they have this behavior, and then we'll see if we can get Oterma's data, Sun and Jupiter's data as well, have them integrated to see if we can see this transition. And then when you do it, you have not a good result. You actually have an escape. And then we investigated a little bit more with some, in principle, arbitrary adjustments. And then we can see that's more what Oterma does. It starts here. We got the data in some moment where the transition is about to happen. Fit it in this model, adjust the velocity by a trial and error approach. But we do have this transition and a transition back to the exterior region. This is the transition of this couple of decades where it's between Jupiter and Mars, and this is the region between Jupiter and Saturn. Okay, but we are not happy because no one likes arbitrary trial and error adjustments. So maybe this could mean that the circular model is not the best one. So maybe we can go for the elliptic model, which is a little bit more natural because the angle between Oterma and Jupiter's orbit is small, but also the eccentricity of Jupiter's orbit is small. It's 4 times or 5 times 10 to the minus 2. But still, we might see that it plays a role. So we went to the elliptic model, so the planar. It's an adjustment, so it will have some effect, but we will handle it. But now we assume Jupiter and Sun move in elliptical orbits. This is a Hamiltonian for this new problem. F is what we call true anomaly. It's a way of measuring, it's a substitute for the time. And also this model can be seen as a 2-pi periodic perturbation of the circular one. In fact, if we set E, which is the eccentricity, to 0 and do some algebraic manipulation, we got the Hamiltonian for the circular problem again. And when adjusting the data for the elliptic without any other adjustment, any arbitrary adjustment, we have an orbit which looks more like Oterma's one. The Oterma enters, stays for a couple of decades, and well, let us give a zoom here in this region. It actually have a behavior that we don't like, which is revolving around Jupiter once, but we will accept it because we'll study just the first of these jumps. We'll accept this error, okay? We'll study just the first transition, the transition from the exterior to the interior region. A couple of words about the elliptic problem. The system of coordinates is adapted. Now, instead of revolving, have a rotation with the constant angular velocity. Now it's a different angular velocity, and they also pulsate, they expand and contract, so that Sun and Jupiter are in the same spot, in the same point. They have the same points, equilibrium points from L1 to L5, and they have the same stability, which is center saddle, L1 and L2, which are the ones that we'll care most about. But now the periodic orbits turn out to be invariant tori, because you have an orbit that is perturbed, and if these are not commensurable, it is a quasi-periodic orbit that lie on different tori. As this model can be seen as a perturbation, everything that we computed in the circular problem might be continuated. We might implement a numerical continuation, for instance, to compute the objects in the elliptic problem, seeing the circular as the elliptic with eccentricity 0. And the biggest difference in this about these two models is that now we have a full 5-dimensional phase space. There is no way of reducing any dimension, because for the circular problem, it's an autonomous Hamiltonian. The energy is preserved, it's constant along orbit, so we might reduce to 3-dimensional submanifolds, and the analysis is easier. But now for the elliptic, it's not possible anymore, and we have a full 5-dimensional phase space, and we should handle it. The way to start handling it is, and it comes from a paper from my PhD advisor, Angel Jorba, which is this paper here. It's defining an autonomous map from the phase space as the time to pi flow. So we have the full 5-dimensional phase space, including the last variable, which is time. I will be referring to time, even though it's not, but we can refer it as time. that repeats itself. Okay, so whenever we define, for instance, a flow from the section, the time section 0, we define an autonomous map, and then we might have we reduce our system to 4 dimensions. So let's see if it helps. The biggest problem here is that this system around L2 and L1 is incredibly unstable. For an integration time of 2 pi, one gets, for instance, for one of the orbits, the greatest eigenvalue of 10 to the 6. And that's not good, because with 2, say 4 pi, we already say we computed all the objects with 10 to the minus 12. With 2 integration, with 4 pi integration, we already have nothing. So in order to solve it, we use a technique called parallel shooting, which is, instead of defining just one time section, we define more than one time section, and then our flow is from one to the other. I will prefer to show it with drawing. So here we have one time section that we integrate to the time. Say we used 4, but then we have 0 from 0 to pi over 2, from pi over 2 to pi, and then we compute everything. Problem. Instead of solving, say, one equation, because if we want to parameterize these invariant tori, in order to solve, instead of solving one equation, we should solve a system of equations. And it increments the difficulty of this problem. That's the price to pay, actually, but the instability decreases a lot. So we implement everything. We use, these are standard computations. We have a closed curve, we have a torus, and then we intersect with a time section. What we have is a curve. We compute a parameterization by Fourier coefficients, and then from these Fourier coefficients, we determine points in the phase space, we determine the system, we integrate, and then we solve the system, and then we determine Fourier coefficients of this solution. I will just skip the computations, but again, everything is explained. It's a standard. Everything is explained in my thesis if anyone wants to give a look at it. And then we now have a parameterization of these closed curves, which represent these different tori that we want to study. Okay. It's not, for us, it's also important to compute their invariant manifolds. By these, we compute eigenvalues and eigenvectors of this system to compute the linear normal behavior of these system. So in order to compute it, we reduce the system and with a new easier way of seeing it, and compute the eigenvalues and eigenvectors of this new system. And again, this is standard, and these are just the computations to see that in order to solve this system, this equation, we can solve this system, and the instability we have here, this number I mentioned, 10 to the 6, now turns out to be the 4th root of it. So in this case, say for instance, 30, 40 or something. Okay, so it's good actually. And this because we used 4 sections. If we have used more, this number would decrease even more. So, okay, what we have stored in our computer is a Fourier series, a truncated Fourier series that approximate for each angle the torus, and some Fourier series that approximate the stable and the unstable manifolds at each point. So in order to have these, we have these, first series, and we compute at each angle to produce this curve here, which is the intersection between my torus and time section. And for each manifold, depending if it is for the positive or the negative side of it, we have a vector that points in the direction of the stable and the unstable manifolds. Moreover, there are many of these tori, so we can compute some of them. We can actually implement a continuation scheme to see that if we can compute not all, but a large number of them. For our purposes, we have used the rotation number. The rotation number is a way of parameterizing the torus. It is how much it rotates from one step to the other. We have used the continuation step of 10 to the minus 4 and the tolerance of 10 to the minus 9. We could have used the more rigorous tolerances, but in some regions it had some problems. And then we used this 10 to the minus 9, but in many cases we could use 10 to the minus 12. It has something to do with some resonances regions that we still need to investigate a little bit more deeply. So for this work, we have computed this amount of tori for L1 and this amount of tori for L2. And we'll see that these are enough for our purposes, but there are way more to be computed. So this is a continuation diagram for these two tori. And these are representations of these tori in the configuration space X and Y. I recall here that these are intersections of the whole phase space with a time section. This one, I think it's time section pi, if I'm not mistaken, excuse me. So that's why we see curves. It might seem that they are orbits, but they are not. They are intersections of tori with these time sections. And for the stable and unstable manifolds, instead of having just one equation of how to compute from one point to the next one, we'll have 4 equations, and that will define in these sections we are using. So imagine this is a time section, this is another one, this is another one, and it's another one. In order to have the instability, shorter instability, if we were not using the parallel shooting technique, we would be forced to describe from 2 to 6 as a straight line and integrate it to have from 6 to 10 as a straight line, which would produce a lot of errors for us. Using the parallel shooting, we can approximate from 2 to 3 at each section, and then integrate to have smaller pieces approximated by these by the flow. I can describe it a little bit more deeply. If someone have questions, please let me know. And then here we have some examples of some manifolds that we computed. These four plots here, they are for the smaller of the tori. We computed some tori decreasing the radius and some tori increasing the radius. If I can go back here a little bit, I'm sorry. We have, say, an original torus. We decrease until the method the method cannot handle it anymore, and we increase until a region that were enough for our purposes. So these are the invariant manifolds of the smaller of the ones that we computed. Of course, this is a computational limit. This family ends in the point L2 and L1 themselves. So here we have an approximation of the stable and the unstable manifolds for pi over 2 integration time, pi integration time, 3 pi over 2, and 2 pi. This is for L1. I'm focusing here on this region here. So I just care about this region here to see better these manifolds. Pay attention that it's like small circles. What happens is that you have your manifolds and we are computing some slices of it. These circles are some slices of this manifold. And then it folds around many times. And it's just an illustration of them. This is for one of the torus, just one of the manifolds. This is the unstable manifolds of one of them. Again, see how it folds itself in a not so trivial way, and also how it escapes, say, this region here around Jupiter. It escapes. And well, we can compute many more, but again, those are just illustrations of it. And okay, what about Oterma? You said that we have this comet and blah, blah, blah. Then you ignored it. And after it, you start talking about elliptic and manifolds and tori. What about Oterma? Can we use this machinery to compute which tori are responsible for this transition of Oterma? Spoiler, yes, we can, but let's see how. Okay, so we have defined 4 time sections, 0, pi over 2, pi, and 3 pi over 2. In these 4 time sections, Oterma is here, 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 and here. So in these 4 time sections, 0, pi over 2, pi, 3 pi over 2. We'll do the computations here in this section because it's a section where Oterma it's closer to the region where it starts the transition, but it did not, it's before this transition to start. Here, it's already went through one of the tori. So we'll choose the computations to be done in this section here. Also, for Oterma's initial data, this is the true anomaly. So yeah, let's see the computations in pi, this is greater than pi. So let's do the computations in pi. Okay, the first thing we can do is see if we can see all these manifolds, how they interact with Oterma in this section, in this time section. So here we have our tori and their manifolds. So here, some manifolds, some manifolds, some manifolds, and some manifolds. These four are four different tori. We took the decision not to plot all of them in the same figure because it would be impossible to see anything. So they lie in the same figure, but let's see them in different ones to see a little bit more clearer what's happening. But it's still hard to see, especially because we are projecting in the configuration space. So let's see if we can, if we have a way of see how these manifolds interact with first Oterma, right? Before, when we were in the circular problem, we defined everything. So these are the manifolds, and let's see how they behave, how they interact with each other. And then we cut it. We defined a point intersection, a spatial point intersection, to see how they, if they intersect, if they don't have an intersection, it would be clearer for us, right? Let's see if we can define something that looks like this section here. If you allow me, here we live in a temporal section. Okay, here we are not, it's not full phase space. This is the temporal section pi. But can we determine inside this temporal section a spatial section with x of coinciding with x of Oterma to see how these manifolds interact with this comet? Well, the answer is yes. And this will be a three-dimensional section that we project in the other three variables: y px, y py, and px py. Just to mention, the purple is the smaller tori, the smaller torus, sorry. The green one is the original one, the one that comes from the circular. And the blue and yellow are two interesting tori, because if you can see here, this point is Oterma. These two, in two of the variables, they already got Oterma behind because these grows, right? So they already left Oterma behind. For YPY, they did not reach Oterma yet. And for PX and PY, Oterma is in between them. So that's a numerical indication. Actually, it's not a proof, but that's a numerical indication that those two might act as good representatives of this transition, of this behavior. These two might be two of the most important ones for this transition. And computing some connections between L1 and L2 torus, we might see that there are different types of behavior as well. We have intersections, we have no intersections. But we are not happy yet because, and I'm approaching the end of my presentation, so please bear with me. We are not happy yet because, well, if someone look at these and so what? And we see Oterma here together interacting with these manifolds. Okay, I see there are intersections and no intersection behavior, but in Oterma, I still cannot see Oterma here. Okay, would it be possible to see Oterma? I will get back a couple of slides. Here, remember that I said that we determine 4 time sections, 0, pi over 2, pi, and 3 pi over 2. And for these time sections, Oterma's orbit is a discrete set of points, right? And we are kind of stuck on it. We cannot see anything more than this discrete set of points. Whenever here, 0, pi over 2, 3 pi over 2, and pi and 3 pi over 2. Whenever I go to 2 pi, Oterma is already here. The transition is behind. We cannot see it anymore. Would it be possible to see it? Well, we should take a step back in this case. We wanted to set the number of dimensions of this problem to less and less. We have 5. If we can see 2, it would be perfect, right? But let's take a step back for a couple of minutes. Let's see Oterma and all of these objects in the full 5-dimensional space, right? In the full 5-dimensional space, Oterma's orbit is a 1-dimensional object. It's a curve, right? Okay, so let's see this curve, and then from it we start cutting dimensions, right? Where can we cut some dimensions? Where can you start to compute these things? Well, these sections here, they were computed using the x of Jupiter, because it's a halfway between the tori around L1 and L2. Recall here, tori around L2, tori around L1. This is Jupiter, so kind of halfway between them, right? So we used these x to see these last computations. So let's integrate Oterma until it has the same x as Jupiter. Right? And this is a simple computation. Excuse me. And now, maybe we can see some stuff, because we can define this time section. We can define these tori in this time section. It's just a matter of having one of the orally representations that we have and integrating until we reach this time section, and see if we can have everything. See if we can compute everything, visualize everything here. And in fact, we can, because here it's an intersection between 2 of the tori, one around L1 and the other around L2, and this red dot here is Oterma. So we integrate until we reach the same x as x of Jupiter, and we compute stable and unstable manifolds of these objects, tori around L1, tori around L2, and then we see how they interact. And then we see that there are some of these tori that Oterma lie inside the intersection of them. And in fact, just of curiosity, this is the complete figure. These 4 here, purple, yellow, green, and dark blue, are the ones that were those ones I was talking about that would be good representatives. And you might argue, oh, okay, so these 2 here, they don't, Oterma do not belong to the intersection between them. That's right. But these two, they do. And you might argue, so okay, so you just can throw them off. Not actually, because there is a problem here, which is codimension. And those are my final words. For the circular problem, these tube manifolds, they have codimension 1. So they divide the space, the phase space, in outside and inside. So whenever particle is inside of them, it will stay inside of them because they divide the phase space. Here, the codimension of these manifolds is 2. So they do not divide anymore the phase space between the inside and outside. Of course, we might expect some similar behavior as it comes from the system that has this behavior, but it's not a mathematical proof. It's a numerical indication of it. For the mathematical proof, we should still investigate it more deeply. But the highlight here is that we have all of the parameters of tori that are good indicators that lead this transition movement of a term. And well, I said those would be my final words, but actually my final words is, as they say, once you are somewhere, try to learn from it. And here in Poland, there's a beautiful tradition that to wish happy birthday, they wish 100 years. So, Hildeberto, I wish you 100 years, 100 lat, and I wish you all the best. Życzę ci wszystkiego najlepszego. And that's it.
Thank you.
Okay, Gladston, thank you for the nice talk. And now I pass it to the audience for questions or comments. Well, I have just a curiosity about your calculations. You use the discrete Fourier transform, right?
Yes.
At some point. Wait, what was the group that was associated with it? I'm sorry. Okay, so I will rephrase the question. Okay.
Okay.
Did you apply the one that uses that is used for circulant matrices? The one with the roots of unity.
Yes. Yes.
The traditional one, right?
Yes. Here,
Okay.
we could have used some more specific ones or some, but the traditional, we didn't use like the fast Fourier transform, or no, we were happy with the discrete and everything worked, and we
That was sufficient, right?
Yes.
All right, thanks. So it was a curiosity. I'm interested in this theme, so yeah.
Yeah, for us it was enough, Maybe it would be better for those that are not good behaving nicely, as I said, for some resonances region, maybe, but I wouldn't. Yeah, I don't know. I would need to think a little bit deeper on it. Right now, I have no answer on, or to say even a couple of words about it. Yeah, we use the standard ones, and they were enough for us.
Yeah, as far as I know, this tradition of applying the discrete Fourier transform goes back to Gauss in his youth, working in astronomy to study orbits. Yeah, so the early 19th century.
Okay.
It's a nice.
Didn't know about it.
Nice to see it once again. It continues, keeps going, right?
Yes.
All right. Thank you for the comments and for the ideas. So anybody else wants to ask a question or make a comment?
Hello, I have one question. I would like to know about the influence of Saturn. Would it improve the observations made or not, or it's not so important?
Thank you very much, Jesus. Yes, it can. It does, actually. As I said, this is not my whole thesis that I present here. I have restricted myself to some parts of it, but there's a whole chapter in my thesis, which is the chapter 3, that I play a little bit with bodies in the solar system. And adding Saturn, taking Saturn out, projecting Oterma in the plane, Sun-Jupiter plane, no, not projecting, whole solar system, take Saturn out and the other planets of solar system. I have some computations there, and the body, the celestial body that plays the second most influence on its movement is, in fact, Saturn. The biggest, how can I say it? The thing that we did, we have computed this transition behavior using these different models. Taking into account just Sun, Jupiter, and Oterma, that there is a time span. If you use the whole solar system, the time span is way more than 100 years. We restrict ourselves to 100 years to see if this transition happens. If we take into account Sun, Jupiter, and Oterma, these time span narrows down to, say, 40 years, if I'm not mistaken, maybe a little bit less. Well, let's keep 40 years. But don't trust me. If we add Saturn, we have some years more. So the biggest influence of Saturn is having this time span wider. It's greater. Okay. The point is to study this model using like models in celestial mechanics. One should go to the, say, quasi-bicircular, coherent quasi-bicircular, or even bi-elliptic, because Saturn's orbit is not circular, it's elliptic. So this would be a line of future research, and there are some indications that this would be a good line of future research, but we have restricted to Jupiter, although we have these numerical indications.
Okay. Thank you.
Okay, thank you. Any more comments?
I have some questions.
Okay. Go ahead.
I have many, but just
Go ahead.
just a few of them. why you choose to include the eccentricity of the orbit of Jupiter, and not, for example, to see if you go to the circular model, but with a special version, because there you have objects with codimension too also.
Yes, thank you for the question. That's a good question. The point is, both the mutual inclination and the eccentricity are small parameters. The mutual inclination is 2.4 degrees, if I'm not mistaken, and the eccentricity is 5 × 10⁻². So these are both small numbers that could produce that produces two other models, which is the spatial circular and the planar elliptic, right? Mm-hmm. The point is that because of experience, both Angel and Carla Simó told me that a good step would be going to the elliptic, because it seems that the influence is greater than the mutual inclination. And also, there are not so many computations done in this model, but for the spatial circular, there are. So it would be a gap here greater than this one. So we took the decision to go. But it would be nice to see if we can also describe it with using the circular model. But I guess the point is that the gap here, not many studies here, and because of experience. Also, Angel told me that it would be better because Sun and Jupiter describe an elliptic orbit, period. They don't describe a circular one, they describe an elliptic one. Yeah. You are doing some projection with Oterma, because you should project Oterma in the plane. But Sun and Jupiter do describe the elliptic orbit, and that those could be the reasons why we went to this direction.
Yes, good reasons. And when you continue the torus, who are your parameters? Because here you don't have Jacobi constant, so you have a rotation number and
rotation number. Those are my
two rotation numbers.
Yeah, because one of the rotation numbers is always 2 pi. Because of the elliptic problem can be seen as a 2 pi periodic perturbation of the circular. So one of them is always 2 pi. The other one that we use as continuation.
So it's a uniparametric family.
Yes.
It's different.
Yes.
Yeah. I see. Good. Mm-hmm. And when you compare the manifolds of the tori of the elliptic versus the circular, what do you see?
I see we have similar behavior in the sense that we have intersection and non-intersection behaviors. If we continue orbits from the circular problem for the elliptic, their manifolds, if they have intersection in the elliptic, they will also have, and if they don't, they don't. Mm-hmm. And yeah, those are the main ones that we focus. Maybe we can also see some further behaviors, but we didn't focus on it. That's a good question, actually. Thank you. But yeah, we saw it. We saw that this intersection and non-intersection behavior.
Yes. And the last question, a curiosity: how is the periodic orbits that you see when you put the eccentricity? Because in the circular model you have a fixed point, and when you perturb by the eccentricity, it becomes a periodic orbit. How large is it, or?
Could you repeat your question, Maisa? Sorry.
You have, in the circular model, you have a fixed point, for example, L1, L2.
Yes.
And in the elliptic model, this fixed point becomes a periodic orbit.
No. That's the beauty of it. It depends on the system of coordinates you use. There are some systems of coordinates that they open or as a periodic orbit. But for the system of coordinates that we used, they are fixed. They continue being a fixed point. The point is that the system of coordinates, we change the system of coordinates. The system of coordinates is not the same for any time. It rotates with different angular velocity, and also expand and contract. So they have this. They call it rotopulsating. They pulsate as well, such that Jupiter and Sun are always stuck in the same points.
Okay. So why you see that small torus? When you continue the family, you are not able to diminish a lot the last torus. It's why I thought it was the periodic orbit.
Yeah. No, it's numerical reasons why you cannot. The computer starts to complain about the size and cannot parameterize the torus anymore. But these are not periodic orbits; these are intersections.
Okay. Thank you. Congratulations. Wonderful work. Very difficult. Very. My God.
Thank you.
Yes, I think so too. Any more questions or comments?
Jair Collier has his hand up.
Oh yeah, I can see it in it.
It was my
Jair,
mistake.
do you want to say a word?
No.
I don't know if he has a question or it's something not proposed.
Okay.
It was a mistake, sorry.
Oh, all right. Okay.
But I love the talk. Congrats, Gladston.
Thank you, Jair.
Yeah. Okay, so I guess we don't have any more questions and comments, so I guess time to say goodbye. Just wanted to wish for Gladston success in the continuation of the project. And to everybody, goodbye, and the word is back to you, Annette.
Thank you. I will stop to record it, so if you want to turn on your cameras to take a picture from today,